All right, I think we can get started. Um, right, yeah, so welcome to this edition of the AI Paper Spotlight, Berlin's machine learning research startup meetup. Yeah, I'm Martin Gensel. I'm a staff machine learning researcher at Merantix Momentum, and today I will be co-hosting this session with Patrick Putzky, who very recently started as a senior machine learning researcher in our team. Maybe also a few words about Merantix Momentum in case you haven't heard of it before. So in a nutshell, we are delivering tech-enabled AI services to clients across several domains, especially focusing on manufacturing, healthcare, and the public sector. And what is, I think, really special to our company is that apart from implementation, engineering, and also AI strategy consulting, we have a dedicated research team which tries to bring research into production. This is also the team that Patrick and I are part of. And also, I think it's worth saying that Merantix Momentum is part of a larger ecosystem, the Merantix ecosystem, which also hosts the AI campus, which is where we are at the moment. And this is really the place where many great AI ventures reside. And I can only encourage you to check out the AI campus and Merantix website and also all the other great events that are hosted here. So without further ado, let me come to our today's speaker. It's a great pleasure for me to introduce Thomas Schnake, who is currently pursuing a PhD at TU Berlin, and he's also a member of BIFOLD. That's a quite well-known research cluster in Berlin. It stands for Berlin Institute for the Foundations of Learning and Data. Thomas obtained his bachelor's and master's degree at TU Berlin and also HU Berlin in mathematics and scientific computing. And now in his PhD, he's working on explainable AI, tailored to specific applications, especially on quantum chemistry and natural language processing. And this already brings me to where we are at the moment, because today Thomas will tell us more about his work. Yeah, and he will speak about extending explainable artificial intelligence towards structured and application-oriented interpretations. Thomas, the stage is yours.
Yes, thanks for the introduction. Quite much things is already said, so it's about explaining artificial intelligence. I'm not sure how many people are familiar with this. I will try to give a little introduction, but in general, I want to stress in the beginning, for me, it's comfortable if you like also ask questions within the talk, right? So you don't have to wait until the end. If something is unclear or if you want to have a few more details on something you see on the slides or something I say, feel free to just like interrupt and we discuss this. One thing for you to get a little bit of a sense of what I'm talking about, yes, it's explainable artificial intelligence, but my current research is particularly focused on like structured data, or particularly like we have graphs, we have predictions on graphs, and then we check whether it's somehow reasonable for us what the prediction, like the prediction is reasonable, but we try to find out whether the model and the strategy of predicting it is somehow reasonable, right? But we go into details about this in a second. Yeah, now it works. So little introduction into like explainable AI. I suppose everybody's aware of like artificial intelligence, particularly about neural networks. So this is my little, this is a little cartoon about what a neural networks looks like. And the idea of explaining artificial intelligence, particularly neural networks, is basically we get some input, which is here blue, and we get some output of the model. And usually it's quite difficult to say, okay, why does the model do this prediction? So in some applications, it might not be very necessary. So maybe your model works quite well on the data you're having. This is all you need. But sometimes it is important, right? When it comes to transparency, some people don't trust models when they just do predictions, for example, because they don't think it's robust. Maybe on unseen data, when usually on the data you trained the model on, it's fine. But what happens if you have unseen data? So it might be out of data distribution. So you are wondering whether your model is robust. And one step could be to just analyze what the model thinks of the data in the sense of explainable AI in order to know, okay, like what is the reasoning of my model, right? So this can be some application to gain trust. One little example, like we come, let's say a bit historically about what people started to be in explanation of a model. So here we have an image. The image shows like this house, the sky, and this viaduct. And we have our like simple convolutional neural network, and we want to predict this viaduct. And the model does it fine, like the prediction is fine. But now we want to say, okay, what are you looking at, right? So what in the image are you looking at? Are you looking at the house? Are you looking at the sky? No, the model properly looks at this both, right? So I would say this kind of is what specifies this thing as a viaduct. So we would say, yeah, it's reasonable what the model says, right? In this specific application, I would say, yeah, I trust the model because it understands which parts of this thing makes it into this predicted class. Often this works fine. So here, just to understand the coloring, and so the red means that we would say it's reasonable with respect to the prediction. So high, like strong red color means basically, so it has a strong contribution to the prediction, right? Blue color means, in our case, it has a negative prediction to the, a negative contribution to the prediction. So you would look, for example, at this part here, this house, and it says, okay, this is like not curvy, it's a like more edgy. So this might be a negative influence on the prediction viaduct. I'm not sure why, but I mean, this is how you interpret it, right? Regarding the coloring, we will keep this coloring throughout the presentation. So good to be clear on this. But one thing is, so in the pixel-wise explanation, so on the images, often this is okay. So we have a prediction. We look at the pixel, and then we say, okay, something is reasonable or contributes positive to the prediction, and some other pixels are not. But often in applications, and we come into this in a second, this is not a resolution which is sufficient. For example, when you only have each values for individual pixel, you're not sure whether the background actually influences the prediction. For example, there might be some correlation between the viaduct, like the part which is now red, and the background. Maybe the background is not really important, but for example, this thing being in the background of, or the clouds being in the background might be important. So there might be some like contextualization or some interconnectivity between these elements, right? And this is not really seen here in this heat map. So sometimes it's quite limited. We go later into other applications where we see it a bit more precisely than in this image, all right? Okay. So as I said in the beginning, we look at structured data in general. I mean, this thing is, we focus basically on a strategy of explaining the models, which is easy to reconstruct in this particular networks. So graph neural networks, I'm not sure if you work with this. Yeah. So you have structured input like networks or something. You get a prediction, and here in these models, you see in a second why. in these models, it's quite easy, or at least reasonable, to construct interactions, for example. And to, I mean, it seems like most of you know graph neural networks, but let me start a little bit with an introduction of them. So they are using graphs, such as molecular graphs or social networks or dependency graph. Here, the dependency the dependency graph of a sentence. But still, even when you use graph neural networks, in practice, they still act as black boxes. So similar as the normal neural networks, you cannot really reason about why the model did a certain prediction, right? So this is what we want to look at. And as I said, particularly on graph neural networks, you have this particular structure where you can recover interactions, right? And I'll show you in a second how it works. First, what we think about of a graph neural networks, this might be a simplified version, but we think about message passing neural networks in the sense that we have always this aggregate step and this combine step. Aggregate means nothing else than, so show it here. So you look at the neighbors in the graph, right? And then you, in one layer, explicitly set up interactions between the nodes in a particular layer. For example, here you start with the input layer, then you do this aggregate step, and you see here the lines, and the lines basically say, okay, so between this atom, for example, and this atom, there's a connection, and therefore in the model explicitly we encode these connections, right? And this is why how we later can explicitly say where the information flow went from one atom, for example, to the other, right? And this combined step, I mean, in practice, this is maybe some feed-forward neural network. And it really depends only on the node, on one individual node. There's no information flow between one or the other node in the graph, right? This is how we think about graph neural networks. And the idea of explaining these graph neural networks is the following. So in a classic version where we had these pixels, let's say we have our graph neural networks on images and we call it pixels, then what we do is to get individual contributions for each pixel, here a J, or in a sense of a network, it would be a node in the network, right? So you would get atom-wise or node-wise contributions. You would look at, in this case, the first order explanation. First order means at some level, first order decomposition, or like the gradients with respect to one node, or one node embedding in this case, with some root points. So in the sense of Taylor decomposition, this would be first order decomposition, and you would then just get for each atom or for each node, for each pixel, one value, right? And effectively what you do is you just focus at the contribution at the input, right? So this is the normal way. This is how you can explain, I mean, normal way is just like the classic version of it. But particularly here on graph neural networks, we can actually know in every individual layer where the atom or where the node has a certain representation. So you have an input representation, then you have some other latent representation of the atom, like in zeroth layer, first layer, second layer. And then you can actually know where the information flows in the forward path. And the idea is just to extract in every layer this chain of atoms, this chain of nodes, right? And in theory, this is nothing else than the high decomposition of the higher order decomposition of the model. So kind of the higher order gradients with respect to, in this case, the edges. So edges, E is one edge. You would have gradient with respect to this edge and this edge. Yeah. Is this clear until now? So this is the core method, right? Yes? Yes, sorry, node or vertex, exactly. Yeah. Yeah, like for me, nodes is like we have the graph and we have edges and nodes or vertices, right? Knoten, exactly. Yeah, yeah. Yeah, perfect. Yeah, that's what I mean. Is it clear, this method, that like the resolution kind of changes? So before we had atom or pixel-wise or Knoten-wise explanations, and now we have kind of higher order explanations with multiple, like where kind of how the different nodes, how the different atoms interact with each other, right? Yes?
Again, so on the left side, you have, let's see,
Mhm.
the layer,
Exactly. Yes, so we would basically track in every individual layers so we specify in the beginning what chain we want to attribute. Like in a molecule, we would just say, okay, I'm wondering whether there's a molecule and we have different atoms, like let's say carbon atom and hydrogen atom, and then we are wondering about the contribution of the interactions. And what we just do is we check all the chains where in the model they interact with each other, and this is then for us the contribution of it, right?
visual dimension is visualization mean like the red axis, right?
So you mean the question? I should also repeat the question, right? So your question is what actually these parts are and what the red parts are, right? So for us, this is the horizontal line is always the latent representation of the individual atom or the individual vertex. So this would be the vector of the first layer. So the latent representation of the first layer of, I don't know, hydrogen atom, right? And this would be then the latent representation in this first layer, or the second layer in this count, also of the hydrogen atom. And the red part is for us only a visualization of what we kind of extract in this formula, or what we extract from the model when we want to explain it. Because it's in our case extracting, because the idea of this decomposition is that when we take the individual terms, for example, when we take the individual terms here, every possible configuration, like R1, R2, and whatever, until 10, for example, then we basically reconstruct the prediction. So when we have an energy of like 10 electrovolt, for example, for a molecule, summing over all the contributions, we get again 10 electrovolt. And this is helpful because we say we reconstruct the prediction in the sense of individual input features. And here we get the same. So we would say when we sum over all possible configuration, like, I don't know, I mean, you have multiple edges there and very many different chains. It's much more complex, but still when you sum over all different configurations that are possible, you again reconstruct 10 volt, like the prediction, right? And yeah, here we basically split the model into like n parts, and here we split the model into many different interactions within the layer. Yeah. Yes.
depends on all of the combination previous.
Exactly, yeah.
That means the deeper the network, the more we have this gradients like me. Slowly, yeah.
Exactly, yeah. So this is, so I repeat the question. So the question is like, when you have more layers, you basically get more configurations, right? And it's exponential with the layers. So you would get some like n, when you have n nodes, you get n to the power of number of layers. Yeah, so it explodes quite fast. For example, when we apply this to models deeper than, I don't know, 5, 6, 7 layers, it won't stop in lifetime, right? So calculating, but this is also one thing, like this is the methodology. And in the second and third parts, we basically show how the computation can be accelerated. So there are little like tricks where you kind of get a interesting and good resolution of the explanation, but in linear time, right? But I come into this into a second. So you already notice what the difficulties, but we still try to solve them, right? Yeah, nice. Yeah. I mean, this is the methodology. I think you might also want to see some results. I mean, we have some, I thought maybe it's easiest to just start with text. I also have results on like quantum chemistry, for example, and some synthetic data, but this is probably the an intuitive way. First, so we consider here like sentiment analysis data, like you have a sentence and then you want to predict the sentiment, like whether it's positive or negative. And we have trained the data on a GNN, like graph neural networks, and we trained the data on like a very simple back of words model, right? So it only incorporates single words. But what we want to stress here is the GNN. So the GNN is definitely better in predicting, but it also is better in understanding the grammatical structure of the sentence. So one example is this not like. So I didn't like the movie. Or in this case, first I didn't like the boring pictures. So the question is, does the model understand that not like is something negative, where actually only like is something positive, right? And we would say the back of what, so first we train everything, we use our explanation framework, and now we see, okay, the back of words basically can only, so it would say not, the word not is negative, and the word like is positive. I mean, and it's a primitive model, but that's like, I think in this case, the reasoning. And in the GNN, we see that the word like, and particularly the interactions to not like, where you can, like, these are basically all the higher order interactions of the individual words. And we see it properly understands that not like and their interaction did not like is fully negative, even though the word like is actually a positive word, but it understands this negation, right? And I mean, first, the model understands this, nice. But second, we can also verify with our higher order explanation framework that it understands this negation, right? And some quantitative evaluation. Sorry. So we went basically over the full data set and just checked for like words or word combination that are very reasonable for positive or negative predictions. And it basically says words like ridiculous or boring, like one token words, they are very highly contribution to the negative sentiment, and others like when you look at, for example, at multiple tokens such as documentary brilliance or is astonishing, full stop, or brilliant. This would be, this has a high contribution for positive sentiment, right? So we would just say here, okay, the model understands not only positive words, but also a positive, like very combination of words that are very reasonable for the prediction, right? Okay. But I think, yeah, to understand more the resolution, probably this image, this tree here is very reasonable. What we would do now, this is one example where in this case, the GNN is not very deep. I think like 2 or 3 layer. You can kind of actually see the depth. So you would count like this, 1. So you see this bow here. So this is 1 walk, and it introduces like 3 words in it. So we have 2 layers, right? In this case, when you have 2 layers, it's fine to compute all the walks, right? But when it gets deeper, there are difficulties. And now we want to discuss it a little bit, how we can accelerate the computation. And and we have 2 options. I will introduce first a bit what it is. So the first option is basically we attribute combinations of words. This can be accelerated very fast. And second thing is we want to compute only single chains that are very highly contributing to the prediction. It depends a bit on the scenario, on the application, where one or the other makes sense. Sometimes you want to have everything. Sometimes you want to have like combinations of words. Sometimes you want to have highly contributing chains. And how this is computed and in what scenarios you use one or the other, we are discussing now, if there are no further questions. Okay, so first step is we want to explain subgraphs. Subgraph contribution is like when you formulate the problem here, we have this small graph. We want to know how high the contribution of an individual subgraph is, right? One important thing is when you have simple, like our pixel-wise explanation, I mean, we can also have some sort of subgraph or like multiple pixel contribution by, for example, just summing over the individual contributions, right? So you have high contribution for, I don't know, here we have a molecule, high contribution for oxygen and nitrogen, then you just sum it up. Okay, then you have kind of the contribution of them both. But in practice, this is not very reasonable, because for higher order interactions, where you really only consider the interaction between, for example, oxygen and nitrogen, the simple strategy has actually no contribution, right? So you want to have the difference between the contribution of them both minus the individual contribution is always 0 in the simple case. But when you have the subgraph attribution method, where you really want to consider all the interactions of the 2 atoms as well, then you get a proper contribution. And you, for example, in the case of a second order like C and N, this would be then a bond contribution, for example. And this is the challenge. This is what is often interesting in chemistry, right? But let's look real quick on the simple specification of or like the definition of the subgraph contribution. The simple way would be here on the left-hand side. So when we incorporate the walks, right, then we would think about this contribution of a subgraph, like a subset of the walks. We would just basically say, okay, let's just sum over all the walks where the individual atoms are present. I mean, it's still many, right? So you still have S number of atoms, like S is this subgraph, number of elements in subgraph to the power of L, so it's still exponential. This is, I mean, the contribution itself is reasonable, but similar to the method itself, it's exponential complexity, right? So what we do is we reduce the complexity by having a little trick, basically. So usually what we do is we have this backbord propagation with respect to the individual nodes, but all we do for obtaining this in one step is to kind of concatenate the the atoms or the elements in the subgraph, and then just like do one backpropagation step, right? So one gradient computation. As you see, so here we usually had contribution of J, K, L, whatever. And what we do is basically we take a super node, like it's a philosophy, it's like just an attribute. So super node means we consider the subgraph to be just like a new node. And then we do the simple contribution of like having always the same subgraph in the chain of the higher order contribution. This is just one gradient step, and it's equal to the other one. So basically, it doesn't matter how deep your model is. This is always very fast, and this is very slow, right? So it's a little bit of a trick. I'm not sure if you are familiar, for example, with graphical models. There are also sometimes these tricks when you know the structure, like message passing frameworks, and this would be then just like the sum product algorithm, right? So sometimes you can reduce particular structures in the graph of a graphical model, and this is one way of doing it. Yeah. Okay. Yes, of course. Hmm? Concentrate information to really you mean no, like imagine you have like two important items. Yeah. And then you put one element in one subgraph, another other. That means you would have more combination than you would have together. Mm-hmm. You mean like not only taking one subgraph, but multiple subgraph in this sense? No, my question is regarding how we get these subgraphs. Ah, so I see. Usually in practice, you know in advance which subgraph you want to consider, right? But if you don't know, probably you should. If you don't, it depends on the scenario. I mean, I'll show you real quick. In this example, for example, I think people would, like a chemist would look at the molecule and would say, wait a second, like individual atoms is not very interesting for me. What I'm interested in is functional groups, for example. And then, I mean, I don't know functional groups, but a chemist probably does. So he would just say, okay, we have here this NO2 or however you call it. This might be a functional group. Let's group them and understand whether only this functional group individually has a contribution to the prediction. So if you don't have this idea of how to group them, probably you should compute all the contributions, or maybe something like all subgraphs of size, I don't know, 2 or 3 or something like this, and then check which one is, for example, very relevant. It's then it again becomes complex, right? Yeah, but it depends really on the application. I would say for a chemist, this makes sense because they really look for functional groups, and often they are not that. It depends on the probably even in the application of a chemist, but at least they have an idea how to group the atoms into functional groups, for example. Yeah. Other questions? Okay. Where were we? I think, yeah, discussed the complexity, and this is only a little just visualization that it works, right? So left is just the time, the y-axis is the time. And here we see when we only have the naive way of computing the subgraph attribution, the time is exponentially large for deep models. So until 5 layers, it's fine, 6, but then it really blows up. Where the computation of subgraphs with respect to the size of the set is just like quadratic when you increase the set size. So this is feasible, I would say. On the other side, when you have this new method, you see the computation time with respect to the layer is just linear. And the computation time with respect to the subgraph size is actually constant. So it doesn't matter. The size of the subgraph doesn't matter. Okay. Yes? Ah. You mean these peaks, these one?
Yeah, but like normally method is like feels like orders of magnitude faster. Like it's not only like the asymptotics, but also like order kind of.
What do you mean with the like here this is exponential, right?
So not only in an asymptotic sense to different networks, also like left
Mm. Yes. So for example, you mean when you have a very shallow model, right? So here, the only scenario where the naive, yeah. So the only scenario, even when you have a size of, let's say, a subgraph size of, let's say, 7, then here you, independent of the layer, you would need 1 backpropagation step, right? But in the naive way, even if you have only 1 layer, you still need 7 backpropagation steps, because you have like for each atom, basically in this case, for each element 1. So it would then increase. Yeah, probably this first one is just like this times size of this set, like 7. I'm not sure how big the size was of the subset in this experiment, but yeah, probably 7 or something like this. Yeah. Other questions? Okay. I mean, this is kind of all I want to say about the subgraph attribution. I mean, we had one example here where it makes sense, right? So one qualitative result. And the rest is basically showing that the computation can be accelerated. Then in the next step, I want to look at another. So we still have the problem of the complexity of the explanation method because there are so many combinations. And another step is to say, okay, we are not interested in the most evidential subgraph, but we are more interested in the chain, which is mostly evidential. We will later, in the last slide, we see the one application of pandemic data or epidemic data, where you kind of search the infection chain, right? Here, in this sense, it makes sense to understand where the highest, like where the infection chain maybe comes from infecting, for example, people here. So it depends, like the connections you're having. Sorry? Super spreaders, exactly. Yeah, you're wondering about the super spreaders. And this is a strategy how to find them fast, right? Before everybody is already sick. Yeah. Okay, but let's start first with the like the motivation. Similar as before, we have the graph neural network, right? And the idea is you have this big graph, and what you want to know is not only like one, like the not to specify in the forehand what subgraph or what atoms or what nodes in this case you're interested in, but you just want to know what are the feature interactions in the graph that are most relevant for the prediction. It might be only a little portion, but still the one which really like points out, right? As I said, so we still have this graph neural networks strategy, graph neural networks model. And the brute force, the naive way is to get the most evidential chain is just to take all the possible walks we are having here, all the possible interactions. And then when you're done computing all of them, you just take the maximum, right? It's very, I mean, it has similar as the other one, exponential complexity with respect to the number of layers. Yeah, it's just a naive way, right? But what we can do is, this is then again in the context of message passing or graph neural network, graphical models. It's like the max product algorithm. And what you do is you don't compute all of them, but you take in every step when you backpropagate, when you do the gradient computation, you don't do them until the end, but you stop. So you start at the outputs, and in one layer before, you basically stop and then decide which would be the most reasonable step from here to here or to the other, right? So what you do is you compute just like in every step all combinations, and then take the step which is most promising, right? In this case, it's greedy, at least in the practice. So there are non-practical scenarios, like there are models where it would be optimal, which are models that are not used in practice. So what usually the problem is, so if these are so latent representation usually has like, I don't know, 124 neurons, right? So it's a vector. In this case, it's greedy to compute the best step, right? If you would only have one neuron, then it's optimal, right? But yes, it's a greedy approach, but in practice it works quite well actually. So it's yes, of course. So you think that you said that yes. So you said the gradient gets smaller the more computations you do, right? Yes, it's definitely true. But it's also true for this one, right? For the left one, is we have the same problem. The gradient always is getting smaller the further you get towards the input, right? But yes, you're right, definitely. But here, in our case, we compute we do this iteration in every layer, right? And then in the last layer, we just say this is our potential best solution for the most evidential walk. Yeah, and then we stop. And this is just like linear time, similar as the other one. For example, in this example, we come to the data in a second. In the example of the infection data, what you kind of would do, like you have all the flights, or let's say the people you shook hands during the day, and then after in the night you notice you get sick, and then you want to check with whom you met, for example. And the idea is not to kind of retrace all the possible. So when somebody shook a hand of the other one, and then this one to the other one, you don't track every possible combination there was. You just ask like with whom did you shake your hand that was very sick, for example. I mean, it's the model does different things, but that's the idea, right? Yeah. So. Mm-hmm. You mean, for example, saying, okay, the first ones we want to compute really all of them, and then in the later layers we just do the step. Actually, we didn't test this. It's a good idea. I like it. I mean, you would probably, it depends also where you expect that this makes sense, maybe at the output layer or at the input layer. Exactly, exactly. So, yeah, true. Yeah, 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 definitely. But one thing, so I don't have the test here, but in practice it was actually okay. So even when we did this as a greedy approach, usually I have to chat for the details, but in most of the times, the optimal solution was within the top three walks, which we had only in this greedy approach, right? So in practice, it's fine. What we also usually do is we don't compute just the most evidential one, but we compute the first like 10, right? And then in one of these, I would say probably like when you have 10, the optimal solution is quite probable within these 10. Yeah. But let's look at some results. I think this is also nice to discuss. We compare them also to other explanation methods. This is the infection data set I was talking about. So basically, it's just like many different, it's a synthetic data. So, but the idea is you have an initial infection. So some people are sick, and then you have a network given where you say, okay, these connections are possible, like kind of the people you shook hands during the day. And then you kind of synthetically predict which knots, which persons would be infected after 1 or 2 or 3 steps, right? I think in our case, it's exactly this. So 1, 2, 3 steps, right? Maybe 3 days, let's say like this. After 3 days, and you have just like specified the people you shook hands with. And here we basically compare the resolution, right? So they're all the same model, but we have different resolutions for the explanation. And the idea is basically just to show you, even though this might be a little bit of an abstract resolution, like these chains, right? In this case, it makes quite much sense, because what you do here on the left-hand side is you show here the most evidential infection chains, which your model would think that's where the sickness comes from, right? Always with respect to the first, this star knot in the upper part. So the star is sick, and then you want to know, okay, where did this infection come from, right? And here, for example, on the left part, I would say maybe somebody can say, okay, maybe I should not meet too often with these guys because they are sick, right? Here, or maybe even like not shake hands like this. I think it's sufficient. On the other side, when you have this not attribution, where you only say person 1, person 2, person 3 has a contribution to me being sick. I would say we want to say it's just less informative, because we know that the infection came from shaking hands, not just from people existing, right? So it's not, here you would, for example, of course, you see individual persons are sick, but it doesn't reconstruct properly where the infection came from. That's the idea. Similar for this edge contribution, where you only consider in just individual interactions, even though maybe some of these interactions are not are only relevant. For example, let's say here 314 actually is not sick, but we're just shaking somebody's hands right before he shook your hand, for example. This means it's not really necessary to avoid the person, because he just like transported the sickness from one person to the other, for example. So I just want to say edge-wise contributions is not always sufficient, because it's always necessary really to retrace the full infection chain. So only individual edges are not sufficient to understand where the sickness comes from. Yeah. Okay. I'm already at my conclusion, which just like recalls everything I said already, right? So what I want to say is that in the beginning, only pixel-wise explanation is not sufficient, right? So at least in particular applications. So we should look at interactions, higher order interactions, all these things. We had the problem of acceleration, like the problem of complexity. So we had a few scenarios where we can accelerate this to make it fast. And also, yeah, the resolution is always a big thing, right? So resolution of the explanation, walk-wise, subgraph-wise, and so on. And depending really on the, so you saw we had different data sets, different problems. It always really depends on the problem and on the data you are focusing on, also on your prior knowledge, whether they are functional group and everything. But if you have this clear, then you can probably construct a nice working and very informative explanation method. Yeah, thank you so far.
Thanks so much, Thomas, for the great talk. Yeah, are there questions? Yeah, maybe.
This is obviously all based on graphically GNNs, graph neural networks, right?
Yeah.
And I'm not super familiar with that, so my question would be not specifically to the talk, but how would you represent music or audio data for use in such a model, if you have any hints? Thanks.
Good question. I mean, audio data or music data on a graph neural network probably is difficult. At least I don't know any model which does that. But yeah. No, I mean, it's a nice question, I think. But I mean, what it is also something I didn't say in the talk, but it's still important because the framework, I mean, yes, we do this here on the graph neural networks, right? But it also works on other models. It also works on, for example, data which works on music and on audio, probably. We should like.
So we could use the method, the LRB specific method on a model. I mean, I was just thinking about it. So if you have an image, we could definitely sit down and identify some graphical structure in the image, right?
Yeah.
More
I mean, this is, it's not here in this talk, but it's a really interesting thing because particularly, so here I talked about chemists, right? So chemists have an idea of how the model works, or I don't know, the people who work on this pandemic data, they have a certain idea how they want to have what they find reasonable to be an explanation of the model. And musicians, they would say, yeah, I don't care for, I don't know, and so when you look at, for example, the time series of the audio, it's quite probably quite noisy, but the spectrogram, this says something, right? So you would say, okay, here are like high notes, low notes, something like this. And so it's not here, but there are explanation methods which do exactly this. So they would say, for example, there is voice classification of, I don't know, so women or men, right? So you say 1, 2, 3 or something like this. Then the model says, is this a woman or is this a man?
I think I've seen.
Yeah. And then they would just say, okay, when it's a man, they look at the low frequencies. Okay, nice, good work. A woman probably a bit more high frequencies, and then would say, yes, the model understood basically what the male and female voice is about, kind of, right? Yeah.
I have one question. These are all local methods, right? You like talking in the image that you showed, it's explaining the contributions for one single image in a sense, like explaining how one person got sick, for example. Do you have thoughts on how this could be turned into something global, like maybe for causal discovery in tabular data or something similar?
The idea is a local method. One first thing I would just want to show. So this is a little bit of a global analysis, right? The right-hand side. So we go over the whole data set and kind of try to understand whether the model in general understands this task well. So I think this might be a first step, but definitely, I mean, the explanation itself or the strategy is always point-wise. So, I mean, we always have an input and then explain it with respect to the input. But I suppose if you have just like multiple inputs and then somehow pool them reasonable, you would get also a global explanation. I mean, probably there are also ideas of going beyond just like averaging heat maps or averaging something on multiple data sets, but probably that's the first step. But in your case, you ask also because you have a specific scenario with this tabular data, or often this helps just to get an idea what this means for you with a global explanation.
Yeah, I think global information can be used to maybe gain more general insights into some process or some chemical properties, for example, maybe not for one molecule, but gain insights into interactions that happen in multiple molecules or something like that. I don't know. I don't have any chemical background. That was just to use your example. But in tabular data, for example, you might be interested in physical relationships between measurements that you've made and that you cannot achieve in local explanations, but you need to have global explanations for that.
Mm-hmm.
But I don't have a super concrete example also.
And one thing, if you want, I hope I have this in the appendix. Yeah, this is first trial. So, I mean, as I said, so when I think about global explanation in this context, it's usually just pooling over multiple data sets, right? And this is also in the molecular case on the right-hand side here, you would say you want to know whether like the kinetic energy between the potential energy between the atoms, if they are reasonable. So usually you would think the energy of a molecule is respect to not like individual contributions of the atom, but probably because they are like, there's a strong potential energy between the two atoms. And here we basically analyze this by saying, okay, we expect that when you have a triple bond, double bond and all these things, there is more energy to like pull them apart. Therefore, the contribution is higher to the full energy. This is, then we would say, yeah, the model basically understood this concept of bonds, therefore globally having an idea of, having a good idea of chemical properties.
Any more questions? So maybe like one more high-level question, somehow related to your question, Max. So you showed us these nice applications in chemistry and also in natural language processing. So what would you say like general like properties or shared properties of the data, underlying properties that make your method work well? And can you also think of like other applications and also maybe applications where it might not work so well? So are there some intrinsic assumptions that you make?
In the explanation method?
Yeah.
Yeah, I mean, there are always new things to explore. I mean, one thing which is sometimes a bit interesting, a little bit of an edge case, I'll show you in a second, wait. Here. So usually what we hope in the for the explanation here on the right-hand side is that the contributions, we hope they are really independent of any other context. So the optimal way is this decomposition that the elements are really independent of each other. And one thing that effectively occurs here is this only is optimal when you have a linear model. When you have a linear model, they are all really independent. When you have a nonlinear model and you still want to recover the property of predicting the full energy, like the 10 volts, that when you sum over all the contributions, you get 10 volts, right? Then there are slight dependencies between all the individual features here. And sometimes in practice, particularly in the chemistry case, this is not wanted because you basically want that when you have two atoms here and the distance of them is the same, only the configuration of the two atoms is the same. It shouldn't depend on the neighboring atoms, but effectively it does. And sometimes there are edge cases where this, so in general, it's very much the same. There are not huge problems, but you see a little bit of noise like this. Yeah.
Interesting. Any further questions? If I saw correctly, there are no questions online. Okay, so if this is not the case, let's thank Thomas again.